complete guide to RTOS scheduling policies. So today we are going to be completely study about the scheduling policies which is happening in your RTOS. So that is what we are going to be completely discuss about this. Okay. So we already discussed about the fundamentals and all the things which is mandatorily we need to know. And so today we are going to be study about the scheduling policies. Okay, what are the scheduling policies it is going to be following? Okay, so yes, first of all, scheduling policies overview. So first of all, how the scheduling policies is actually going to be happens. Okay, in the multitasking RTA system, scheduling policies determines which task runs next when multiple tasks are ready. So actually, so why the scheduling policies which is comes here it is whenever the RTAs can able to do the multitasking. Okay, so whenever it is actually going to be do the multitasking, it need to know what the task going to be runs next. So what the task should be ready for to run. So all the thing is going to be determine that. Okay, so here we can able to scheduling based on the priority number kind of thing. Okay, so the scheduler is one of the main important parameter in your RTOS kernel. Okay, which helps to deciding what is actually going to be runs next. So I already told you this concept. If you are having an operating system, okay, so if you are having a operating system, so the very important parameter on your operating system is your kernel. Okay, so what it is your kernel, right? So inside the kernel, the very important parameter you need to be understood is that is a scheduler. Okay, so your scheduler. So because this scheduler is one of the very important parameter, it need to be finding out, it need to be schedule what task is actually going to be runs next. All the stuff is mandatorily. Okay, and here how it is actually going to be scheduling. Okay, here scheduler is one of the part in the kernel, so which helps to deciding it for execution. But in what matter, so in what basis it actually going to be scheduling the task? Okay, so first of all, it is based on the priority number and states. So the timing, that means periodic state and deadline based, and fairness and latency requirements. So finally, the goal is efficient CPU utilization plus meet timing deadlines plus predictable task behavior. That means deterministic executions. So what you are trying to be telling here it is, I need to be scheduling the task, right? So I'm having a multiple task like this. I need to be scheduling a task based on my conditions. What are those conditions? Based on priority number, based on state, what task state, and timing, fairness or latency number. So if you are going to be do that, so you are going to be this is the goal. So you are going to be utilizing the proper processor, you are going to be utilizing the CPU properly and meeting the deadlines and the predictable task behavior. That means deterministic execution. So you are going to be based on all those parameters, it is going to be work. So priority number means, so I'm having a task 1 here. Okay, here that is my task 1, and this is my task 2, task 3, task 4, and task 5. So before that, every task it does having some priority number, or if you are feeling so your task going to be happen first, you can also give your manual number also. For example, here this is how your task has been allocated. Same number. Okay, here this is your priority number. Okay. So I already told you the concept. In it is the based on your RTOS, it is going to be vary. Okay, if you are using a free RTOS, if you are using a free RTOS, the lower number, like 1 is having a high priority comparatively of 5. Okay, the less number it is indicating the high priority. When you just go to this ThreadX kind of RTOS, it does having higher priority, it is having a higher number, it is having a higher priority. Okay, so the numbers only, the numerical representation it is called, guys. Okay, so here I'm having 1 is higher number, higher priority comparatively of 5. Okay, 1 is higher priority comparatively the 5. Okay, but if you're just using this kind of ATAs, the higher number is higher priority, comparatively the lower number. So the numerical expression you're going to be based on your ATAs, it is going to be varies. You're going to be think it. Okay, and this is how I have been given the priority number. For example, I'm using a free ATAs only. Okay, I'm using a free ATA. So the based on the priority, it is fine. So I have been allocated with a priority number, and then you're going to be state. Okay, so if you're just creating one task means whether what the state is, it is running or ready for this task or blocked state, you're going to be find out. And numeric task, that means if you're going to be allocating one task, you can also allocate based on the periodic time. So two tasks which is having a less deadline. Okay, so based on that, you can able to segregate. I'm going to be teach you in the upcoming slide. Okay, and latency requirement. So the latency means we already discussed about the latency. If I execute this task, okay, now the time is I'm going to be execute the task at the 1 millisecond. Okay, sorry, exactly. I'm going to be start the task at 6 7. So the task has been 07 23 second. Okay, the task has been executed, started to be executed at 33. So this 10 second, the 10 millisecond delay, the 10 second delay, which indicates called as a latency. When you have started your execution, okay, when you started actually started your event, and when it actually started the execution. Okay, when you started the event, difference between when it actually started to be execute, the difference between these two, it is called as in the latency. Okay, so different type of latency we already discussed. So based on that, it is going to be you're going to be allocating the task. So this all can able to do the efficient CPU utilization. Okay, so this is the common thing we need to be understood what is inside that, and these are the parameter tests. Okay, and another scheduling. So what we are actually going to be first to discuss about the in scheduling is first of all preemptive versus cooperative scheduling. Okay, this is one of the major important thing you need to be understood. What is mean by preemptive and what is mean by cooperative scheduling. Okay, so the preemptive scheduling means, first of all, we are going to be discuss about the cooperative scheduling. What is meant by cooperative scheduling? First, we will discuss about the what is meant by cooperative scheduling. Okay, the task voluntarily yield CPU control using function like task kill. The scheduler runs only when the current task gives up the CPU or blocks or waiting condition. Okay, so no forced interruptions by our task. The thing is, you are going to be consider. I'm going to be do the cooperative scheduling. Okay, I'm going to be do the cooperative scheduling means, what is meaning of cooperative scheduling means, so when you have been allocated the task like with a priority number, you are going to be do like this. Okay, when it is a cooperative scheduling, when this task one has been totally completed, then only just move to this task two. When the task 2 completed, just move to task 3. Okay, even any external interrupt, so any emergency higher priority task, okay, higher priority task trying to be interrupt. For example, 0 is the higher priority here. Okay, it is trying to be interrupt. It is never trying to be get interrupt because it is called as cooperative scheduling. In this cooperative scheduling, you can't able to get interrupt with this. Okay, so it doesn't get interrupted by any external higher priority because it is a cooperative scheduling. Once the task has been completed, it just move to this next task. So it is a, like a it just one after another. So once you have been completed this task, next. Okay, even higher priority task is trying to be interrupt. It is not going to be interrupt. Okay, no forced interruptions by our task. Example. Okay, so here I need to be done the task A. Once the task work has been done, so do the task A. It is going to be do this task A. Once the task been done, then it is going to be allow for this task B. Okay, so just a simple example. And what are those advantages in it? Okay, first of all, it is simple to implement. Okay, so there is a low overload. That means you're not going to be overload the staff, because this is the task. Only I'm going to be give the 5 tasks. You're going to be complete one after another. So it does not get any overloaded task in it. So it is very simple to be implemented. No need for complex context switching logic. That means we know that what is meant by context switching. Context switching is like when the task is currently working. So I told you, like when a higher priority task is trying to be interrupt, this task is going to be do. So you just consider, guys, this is my task. This is the task I'm doing currently. Okay, current task. Okay, this is the higher priority task is trying to be interrupt. This task one currently stop. What it do? It just stop and save your contest, right? Because if it is actually executing some works process, it has been done half of the work, like 50% of the work has been completed. Because of this higher priority task get interrupt this one, it need to be stopped. The 50% of work, where it actually going to be stored? It is going to be stored in your registers, right? It is going to be stored in your register, right? So this is called as a context switching. So it is going to be stored into the registers and then come to this work on this higher priority task. This is happen in your context switching. But this work is not going to be happen because it is like a periodic task, like one after another one. Okay, and a task cannot be interrupted. Yes, it can't able to be interrupted. So good for predictable critical sections. And disadvantages. So if you are going to be use this cooperative task, and what are the disadvantages you are going to be feel is the bad task never yields can block other CPU starvations, and responsibleness to external event is poor, no ideal for real time. That means it is not good for ideal. Okay, so in our task, what does mean by our task? Okay, so if it is higher priority task trying to be interrupt, we know that example called as an airbag. Okay, so we are having a car, so we are having a car brake and the music will be runs. So all it has been considered as a task. Okay, so if everything is going to be run one after another, if higher priority task of airbag is trying to be interrupt, it can't able to respond it because it is a cooperative task. One after another only it is going to be do. This time it is not good for this real-time operating system. It is very bad for this external. It is the responsible is very poor because it is not going to be responsible for the higher priority task. Okay, and yes, so never going to be yields means, so if the task one, okay, if the task one has been completed completely, so if it is complete, the task one has been completed fully, then only just move to this task two, until unless it is not going to be touch any other task in it. Okay, I hope you got clear. And next we are going to be discuss about the preemptive scheduling. So what does mean by preemptive scheduling is the RTOS kernel can interrupt the running task and switch to another higher priority ready task anytime. Okay, so here itself we can see the difference of those two achieved via context switching triggered by the interrupt system timer or kernel event. So it is reverse, guys. So if you are uh, just study about this preemptive task. So what is meant by preemptive task? What is meant by preemptive scheduling, guys? The preemptive scheduling means it is different because if the task one is running, it just move to this task two. Meanwhile, if higher priority task is trying to be interrupted. Okay, if the higher priority task is trying to be interrupt at this time, it just stop here. Okay, it just stop here, and all this contest has to going to be, if it is done the 50% of the work, it is going to be stored on the registers and then move to this, give the priority to this higher priority task. Okay, it is different. So in this RTOS kernel, when it is the preemptive scheduling, when it is interrupt, okay, if the task is running, it just switch to the another higher priority task ready at any time, okay. So achieved via the context switching. Context switching is just storing the data. If it is trying to switch from task 3 to task 4 means, so what it actually going to be do is the half of the work has been done on this task 3. So the task 3 content, all the data is going to be stored on the registers, and then it just move to this task 4. So save and restore this task 4. Started to be execute the task 4. This is actually going to be happen in the context switching. Okay. And what are the examples? So if you just see the example, currently task A is priority number of 1 and a task B priority number of 5. Okay. If task A runs and interrupt wake up task B, RTOS preempt task A, CPU switches to task B. Same thing. Okay. So here just taking example of task A and task B. Task A currently running. So when task B is interrupt this task A, just to stop this task A and move to this task B. So this is what it actually going to be trying. Okay. Preempt means that is the meaning, guys. So it just stopping the current working and move to this higher priority task. Okay. And having this preemptive scheduling, what are the advantages in it is, so you are having advantages of high responsiveness. That means you can get the super responsible, right? So if it is higher priority task, like if a hairbag want to be uh, giving some asking for higher priority task, yes, it has having the good high responsible. Okay, ensure higher priority task always get the CPU quickly. Okay, so higher priority task is coming, so CPU will be quickly go for this higher priority task. The deterministic timing is ideal for our task, so you can also determine the time. And at disadvantages. So what are the disadvantages in it? Yes, slightly more complex. Why? Because it is context switching. So if you're just thinking, if it is happen in one task is fine and good. Okay, if it is happens at many tasks, if it is trying to be switched to 3 to 4 or 4 to 5, so again the higher priority task is trying to be interrupt. All the data it is going to be stopped. It is going to be store the data on the register. Store the data on the register. So if it is more complexity of the data need to be stored, so the context switches get overhead. This time it is slightly looks complex. Okay, and then need to handle shared resources. So it is also going to be make a problem in mutex and semaphores because race condition means, so same thing. So I need to be storing the data here in this context switching. And what is mean by mutex, guys? What is mean by mutex? So mutex means we already know that if task A is currently running, it needs some shared resources. Okay, if I'm currently running this task A, this is my task A. If I want to be run this task A, what it actually needed? It needs some resources, shared resources we call it as. Resources means it needs some data. Okay, if like task A and task B, it is trying to be do at the same time, need to be handled the multiple things. So at the time the race condition is going to be happen. So RTOS, like you can able to implement it this preemptive functions in free RTOS and VxWorks and ThreadX, and so you can implement it all do stuff in it. Okay, we are going to be completely work on this free RTOS, okay, in upcoming sessions. Yeah, so race condition, yeah. So here guys, we already discussed about the mutex. What is mean by mutex? Yes. So what is mean by mutex is, so task A and task B, task C. So this is how it just allocated in your operating system. Okay. So we know that why we have been introduced this mutex. So if I'm going to be trying to be process this task A, okay. So all the tasks, so if I need to be process this task B also, C also, A also. Okay. If I want to be run this task A, it needs some resources. Resources means data from your registers. So where you're actually storing your data, we already previously discussed this, right? So you are trying to be storing your data on the registers. Registers means we already discussed about lot of registers. You are having a stack, and you're going to be storing your data in stack and many CPU set registers. In that, general purpose registers, special function registers, you are having instruction pointer kind of many registers in it. So all the data is going to be stored on this register. Okay, so in this case, okay, it has storing the data on the registers. You just think about it. The B is also trying to be store the data, is trying to be access the data from this registers. C is also trying to access the data. A is also access the data. But now I want to be run the A task only. We already discussed about the states of tasks. What are the states? Running state, block state, ready state, waiting state, termination state. Okay. Now I only want to be run this task here. Okay. And here, this time, if I want to be run this task A, it should only access all the data from the registers. Other should be can't. Other shouldn't access the data. This time, here we are introducing the concept called as a mutex. So the mutex is like a key or just a lock. Okay. So if you just put a lock for this task A, only the task A can able to access all the resources from the registers. So others cannot. So if the mutex can able to put it on this B, so B only can able to access the task. So if it is happens in the C, C only can able to access the task. So this is what the mutex is actually going to be happens here. Okay, so if it is a preemptive which is happening here, okay, what is actually going to be happen? It is suddenly switch. If it is higher priority task of T is coming, if it is trying to be switched from here to here, so this time the race is going to be happen because it is going to be store the task and it is going to be utilizing the data. And kind of this preemptive is happening very complexity, it is happening very intensively happening. This time it is going to be accessing the data. This time the race condition. That means all the task is trying to be getting the resources from the registers. This time it is called as a race condition. Okay, which is happening in the mutex. Okay. And here, next we are going to be discuss about the priority-based scheduling. What is meant by priority-based scheduling is, so this is the heart of most RTOS kernel. Okay, so this is the priority-based scheduling. The concept of this priority-based scheduling is each task is assigned a priority number. So we already know this concept. Okay. So what is the difference between registers and it is completely different, guys. Okay. So the registers is different. Registers, we are having a different kind of stack registers only going to be storing the data. So the PCB is also going to be different. So it is the complete thread activities it can able to process on this PCB block. Okay. So here, now we will switch back to this art of this RTOS kernel. The concept is each task it is assigned with a priority with a number, like a numerical value, right? It is assigned with a numerical value, like 1, 2, 3. Based on that, we can able to segregating what the when it is actually going to be run. So scheduler always run the higher priority task ready, okay, because it is going to be runs first. And then what are the rules in this priority based scheduling? So if it is a priority based scheduling, the thing is you're going to prioritize with a numerical number, like putting a number like this. Okay. So, and then you're going to be process the data. And what are the rules in it? If higher priority task becomes ready, it permits the current lower priority task. That is a very, very important rule in it. Okay. The task of same priority can use the round robin technique. So this is also, we already know this concept. Okay. If it is higher priority task, which is coming, guys, of Just see this one. There is a three fingers there. I'm going to be so first of all, this is the priority based scheduling. Okay. Here I'm having a task one, task two, task three kind of thing is there. So if it is a this is the lower priority task currently running. If it is comparatively this one, if it is higher priority task is coming, stop and move to this one. This is commonly happen. What is meant by round robin technique? So when we are going to be using this round robin technique, so this round robin technique which is happens in the same priority number. So if you are having a task of task 1 and task 2, okay, both the task 1 and task 2 have a same priority number, task 1 and task 2. So it is having a 3 and it is also having a priority number of 3. So when it is having a same priority number, I can't able to schedule like this. I can't able to schedule by 1, 2, 3, 4. This time I need to give the priority for both the things. Here you can introduce the round robin technique. What is round robin technique? It just time quantum. It is going to be scheduled. It's just sharing the time. Okay. It's just sharing the time. So we will discuss about this round robin technique again. And then task waits and input and output delay or events or in blocked state and won't run. Okay. So even this round robin technique is going to be happen. So one for another condition, if it is having a both the same priority number, what it actually going to be do? It is going to be one should be wait. Okay. One should be for input or output, one should be wait. That waiting state it is called as a waiting or blocked state. Okay. So this is another criteria. An example scenario, if you just see this example scenario, here you just see this concept. Yeah. So task 1, the priority number is 5. It is currently running. Okay, running action. Task 2, it a priority number is 3. So it is ready for this when it is just waiting condition. Task 3, it is higher priority comparatively the current running task. This time it is ready to be preempt the task 1. So this is how it is going to be 2. Okay, this time the task 3 becomes ready. It preempts the task 1 immediately. And free RTOS example. So here you can able to see this. So this is how we are going to be write a code in upcoming sessions. Okay. So you are going to be create the task name A, and it is the priority number, task 3, priority number 3. Okay. So we are going to be see which one is preempts the task. Here task 3, task B, the priority number is 3, runs before the task A. Okay. So here the difference is here the task 3 is higher priority, so it is trying to be runs the task 3. Okay. And what are the advantages in it is? It is the deterministic is high priority task always served first and very suitable for embedded system. Okay. So this one is deterministic is higher priority task always served first. So we can able to predict it very well. Okay. And disadvantages is the risk of priority inversions. So lower priority task holds the resources needed by higher priority task. So in some cases, it can able to bring it to the uh, inheritance. So priority inversions problem might be happen. So what does mean by priority inversion? So we are going to be discuss about this one and a solution for this one. So many people not aware about this priority inversion. So I'm going to be tell you that the solution is okay. So if you are just doing this process, guys, the priority based scheduling, in some cases it can able to happen this priority inversion. To avoid this priority inversion, we can use the priority inheritance or priority ceiling. So temporarily boost your lower priority, higher priority. So now I'm going to be telling you that what is priority inversion and why it is happening, and what is a priority inheritance, why it is happening. So the problem is priority inversion. The solution is priority inheritance. So what is meaning of priority inversion is in a preemptive task. So all the people have been clear up to this point, guys. What is meaning of cooperative? and preemptive task. Okay, because you just remind all the concept topics on your mind. When the preemptive are tasks, when higher priority task becomes ready, the kernel immediately preempts the lower priority task and give the priority to the higher one. This is called as a preemptive task. That is good for responsible because higher priority task is getting good. But when shared the resources all involved when things goes wrong. So why it is actually telling like this? Okay, so when you try the mutex problem, I told you the race condition is going to be happen, right? So this is the thing. So the scenario here, you just see the scenario. The task, this is called as a low task one, using a shared resources. Okay, uh, it is a scenario just happening like that, and then medium task here. Okay, and doing next one and higher priority task is also need this resources. Okay, we just go with the step-by-step sequence. Example, you will clearly understood this concept. First of all, this lower priority task. That means it is already scheduled this task. Okay, so here I'm having guys, this lower priority task is currently running. Okay, here if you just see this one, sorry, this is the task, lower task. Okay, so I already scheduled it. Okay, but I don't know whether it is lower task. So because I already scheduled, this is the task when, but accidentally some external task is coming. So that is higher priority task. Okay, this is called as an, sorry for this one again. So this is the lower priority task, and this is the this task is high medium priority task. Okay, and suddenly the higher priority task is trying to be preempt. Okay, suddenly the higher priority task is preempt. I already scheduled the task like this, lower priority, and this one is a medium priority. Okay, and this time what is actually going to be happens here it is, so the low task starts and lock the shared resources. Okay, so this time I didn't expect this one, so it is lower priority, but suddenly the higher priority and medium priority is trying to be interrupt. Okay, here you just think about it. I only scheduled the lower priority. These two is trying to be preempt. Okay, the preempt, it is trying to be preempt the task. Okay, what is actually going to be happen is it starts to be lock all the shared resources only for the lower priority task. Why? The mutex is only for your lower priority task. Once it has been completed, you just move to this medium priority. Okay, so it is never going to be try to come to this higher priority one. So higher priority task wake ups and it is preempts the lower priority, right? But when higher priority try to be uses this UART, it is going to be blocked because a lower task it holds the mutex. So currently this is running state, this is ready state, and this is also going to be ready. Because it is a preemptive task, definitely going to be give the priority to this higher priority one. But currently the mutex is ordered by this lower priority task. So when it is releases the mutex, then only it is higher priority task is getting one. This one. Okay. But because of this priority inversion, what is actually going to be happens is now the higher priority task is waiting. The scheduler looks for the next ready task of medium task. So CPU switch to the medium task. The result is the lower task can't run. It just moving to this one. So higher priority task is also not going to be run. Medium is running happily. Okay. So higher priority task is stuck waiting for lower priority one. So this is called as a priority inversion. So I think I'm going to be tell it again, guys, so you don't get confused. Okay. So I'm simply telling you. So I'm having a task. Okay. So currently the mutex which can be ordered by the lower priority task. Okay, so currently which is having a lower priority task. Okay, the higher priority task is currently trying to be preempt. Okay, trying to be preempt. Yes, it can able to do it because if it is a preemptive task, it can able to do it. But the mutex who are accessing the mutex, he or that only can able to accessing all the resources in the registers. Okay, when the mutex, it's which is releasing by the lower priority task, and who is taking the authority of this mutex, he can able to accessing all those stuff. Currently, if it is a priority inversion technique, what is actually going to be happen is the mutex is currently holding this lower priority task. It is in the currently running state. Okay, currently running state. Okay, and the medium priority is in ready state and higher priority is also in the ready state. When the mutex, if it is happening the priority inversion technique, okay, priority inversion, when the lower priority task has been completed, because it's just holding the mutex, it is trying to do all the tasks in it. When it is completed, it just move to this medium, next one. It is trying to move to this next one. Even it is trying to be a higher priority task is coming. No. So the mutex is trying to be releases. It is medium priority is trying to be get the mutex. So it's still waiting or get blocked. Okay. So this is called as a priority inversion technique. Okay, here this is all same thing I have been explained here. So the lower priority task starts and lock the UART. So here why I mentioned the UART is the task is I'm going to be configure the UART. Okay. So for what are the registers which are required for my UART protocol? What are the data which is required for my UART protocol? It is collecting in my lower priority task. Okay. And it was locked. Mutex, it just locked. Higher priority task wakes up and it is higher priority when it is trying to preempt the lower priority. But when higher priority task is trying to be used the UART, it can't. It will be get blocked. Okay, it's still holded by the lower priority task. Now, higher priority is still waiting. The scheduler looks for the next one because I was scheduled the task. I was scheduled the task like this, after next. This time it can't able to preempt. It can't able to hold the mutex value, right? So it go for this next one, medium priority, CPU switch for the next one. So once it has been completed, H can't able to preempt. The medium priority is now running. Higher priority task was stuck right now. It is called as an priority inversion. So to avoid this, why we need this priority inversion is here we need the priority inversion because to fix this mess, we are introducing the priority inheritance. What it does is when the higher priority task is waiting for resources yielded by the lower priority task, the resources temporarily boost the lower priority task to the higher priority level. Okay. This time, what is actually going to be happens here? It was scheduled the task like currently the lower priority task is 1. The medium priority task is 3. Higher priority task is 5. It is fixed. The schedule is fixed. I already scheduled the task like this. Okay. This time, after this task, you are going to be run this one. I've been scheduled like this. This time, it can't able to preempt. To inheritance means priority inheritance means it just boosts the lower priority task to the higher priority level. So temporarily, we can able to elevate the priority number to the level of higher priority one. If it is a priority number of 5, I'm going to be elevate the number of 5. This time, both are same. So it's just taking like a round robin technique. So it is not exactly. So when the higher priority task number is 5, it is trying to, yes, this is also high. So it just automatically switch to 5 instead of 3. Okay. And so now the lower priority task temporarily important. The medium priority task no longer preempted. So the lower priority task runs quickly and releases the mutex. Once it just releases it, it does move to this normal lower priority. That means, so that the actual priority number is 1. So I need to be elevate the value number. It is called as in 5. Why? Because I need to be run the higher priority task. I need to be get the mutex log. I need to get all the resources for higher priority tasks. So that's what I just changed it from 1 to 5. So when the task is switched to the high priority, again, it just moved to 5 to 1. So again, it just switched to 1. So once it has been completed, the higher priority task, it just moved to this medium priority task. Okay. And it gets the mutex and continues it. Okay, so this is what which is happening. This is a problem. The priority inversion is the problem. So to avoid this, we are going to be introducing the priority inversion. And then we are going to be discussing about the round robin. What is mean by round robin? Yes. So it is used when multiple tasks is having a same priority. I already told this concept, right? So you just take each task, get a fixed time slice called as in quantum. Okay. We will see this concept on here. So I'm having a two tasks. Okay. So what is the task name? Here the task of same UART as came. Okay, both are UART. The task priority number is 3. This time, which one I give the priority, higher priority one? Both are having the same priority. This time, I'm going to be use the round robin technique. What it is? Round robin technique. So this round robin technique, which is helps to time slicing. Okay, so whenever you are having a same priority task, okay, same priority task, it is slicing the time. So here, this task 1 taking a 10 millisecond and this task 2 taking a 10 millisecond. Once the task 1 has been completed with this 10 millisecond, you just move to this task 2. If it is not completed with this duration, even whether it is completing or not, when it has reaches this 10 millisecond, automatically move to this task 2. Okay. And once it has been completed or not, whether it has been completed or not, it is not going to be considered when the time has metered this line. So it just automatically move to this again task. So it just repeatedly happened this task 1, task 2, task 3. This is called as a round robin technique. Okay, after the time expires, the scheduler give the CPU to the next ready task of the same priority. So this is what I have been explained. Okay, so the time, once the time has been expired, it automatically move to this next event. Okay, and examples in it. What are the examples? Task 1, task 2, task 3 are all are having a priority number of 2. So time is going to be sliced by 5 milliseconds. So each task which is going to be taking a 5 millisecond. CPU going to be switches at every 5 millisecond. Okay, so this is actually going to be happening. What are the advantages which is happening in the round robin technique is fairness among equal priority tasks. Because it is not going to be considered with the based of priority number. It is considering the time only. Okay, prevents one task from dominating CPU. So even the priority number is same, it is not going to be dominated by one another one. It's simply putting a scheduling the time with some certain time. Okay. And what are the disadvantages in it? Okay, what are the disadvantages in it? It is having a less deterministic for hard real-time uses. Okay, and the context switching is overhead if time slices is too small. So it is having a let deterministics because I can't able to determine deterministic. So what is the meaning of deterministic, guys? I'm going to be determined when the task has been created, when it is going to be completed. That is called as a deterministic, right? I can't able to predict it here because the time has been sliced. It is going to be varies. It can't able to predict it, right? And then context switching is overloaded. That means it is the time is very small. Like if I'm just slicing the time of 1 millisecond, here you just think it if it is the 1 millisecond, the contest the task has been not completed, automatically switch. If it is trying to be switched, you need to be store the data on your registers. So same thing, if you need to be store the registers, your data on the register when it is switching the task. If it is continuously switching the task one after another, the context switching has been get overloaded here. Okay, so that has been happening here. Okay, it has been overhead and examples of this free ATAs enable with. So we are going to be time slicing. So we are going to be use it on the practical session. Okay, and next we are going to be discuss about the rate monotonic scheduling. Okay, so we already discussed about the overviews of everything. Now we are going to be detailedly discussing about this concept. What is mean by rate monotonic scheduling? Okay, so rate monotonic scheduling is an advanced real-time scheduling algorithm. Okay, because it is completely based on the timing and deadline based. Okay, the rate monotonic schedulings are, first of all, it is a static priority scheduling, guys. Okay, so it is very static. So we know the meaning of static and dynamic, right? So you just think, keep it on the mind. Rate monotonic scheduling is a static. Okay, so here what is actually going to be do here it is. So it is shorter period task. It is having a higher priority. That means I am having one task, task A and task B. Okay, it is static. Static means if I'm before I'm going to be started to run this task, I need to be do like, okay, this is the task A and task B. Okay, here it is static means before I'm going to be scheduling the task, I need to be check what is the total time going to be taken by task A. If it is a 5 millisecond going to be taken, what is the total time going to be taken by task? It is take 10 millisecond going to be taken. What is like task C? What is the total time going to be taken? It is 3 milliseconds. So first of all, before going to be run those tasks, okay, so we need to be check all those stuff. Okay, so these all the technique, guys. It is not always using any of the techniques in it. Okay, the round robin is one of the scheduling method, and the preemptive is one of the scheduling method. Priority based is one of the scheduling method. We are having the multiple based of scheduling methods in it. Okay, here the rate monotonic is one of the scheduling method. Okay, here you just see it that the shortest task, period task is having a higher priority. If you just check out the thing, I'm having, for example, this is ADC, this is LED blink, and this is a UART data I'm going to be get. If you want to be get the task Z, it's just going to be do the I2C. It is going to be done the task 15 milliseconds. Okay, you are going to be check all those tasks and what is the actual time is going to be taken. So which one is going to be taken very shortest time? So the task C is going to be taking very shortest time. So it is going to be give the high priority to this task C. This is called as a rate monotonic scheduling. Okay, and then it is going to be scheduling the task A. Okay, this is first and this is second, and then it is going to be scheduling the task B, and then task Z going to be scheduled. So based on your time period going to be taken for each and every task, if it has look out this point, it is called as a rate monotonic scheduling. Okay, and the consumption, oh sorry, assumptions. Okay, so here I need to be tell you tasks are periodic, so repeat every task based on the deadline, end of period, so task run is now. And here if you just having this one, task 1 the period is 10 millisecond, task 2 20 millisecond, task 3 50 milliseconds. If you just see this, which one is going to be completed very soon? Task 10, so it is having a higher priority. Task 2 medium, and finally 50 millisecond it is having a lower priority. So task 1 runs most frequently, which is higher priority one. Okay, and what are the pros in it? It is simple and predictable. Fixed priority is equal to easy implementation, because we already discussed about the fixed and dynamic, right? Fixed priority and dynamic priority. It just comes under the fixed. It is called as static priority. Okay. So because we are going to be fixed before going to be scheduling the things, we are going to be fixed. This is the way it is going to be run. And what are the cons in it? Or not always optional. Sorry, optimal, can miss the deadlines even in some use cases. Okay, utilization so works well only for the periodic task. Okay, so if it is happens like this, okay, Like if it is based on the time it is taking scheduling the task, it might be missed out the some deadlines. Because of this task is it can able to miss the deadline. So it is might be happens here. Okay. And then we are going to be discuss about the earliest deadline first. Okay. So if your task is currently running, so it comes under the dynamic priority scheduling. I previously told this rate monotonic, which comes under the static priority scheduling. But this earliest deadline, which comes under the dynamic priority scheduling. Okay. So how it is going to be scheduling the task is task with earliest deadline, it is going to be taking a higher priority. Okay. We will see the example. So here just see this one. The task one, the deadline is 10 milliseconds. Okay. So the task one is 10 milliseconds. Okay. So the priority means, yes, we need the priority. If you just see the real-time applications like nuclear reactor in your airbags, okay, in nuclear reactor, airbags, in mobile applications, kind of many in embedded medical equipments, all must be having this RTOS. Why? Because if I done one task within this time duration, I need to be prioritizing that task in it. Okay. So that's what we are just prioritizing the task. So if you are having a car, inside this car, we are having a airbag, we are having a brake system, we are having a music applications, kind of many, we are having a sensor. So the airbag is very, very important. The brake is very, very important comparatively the music player. So you are having one application. Inside this application, which one is having a more prioritizing? So that you are going to be prioritizing the task is very, very important. That's what it is going to be mainly going to be used. Okay, got it clear? So in example, guys, for example, you're going to be see for the earliest deadline first. You don't confuse with this rate monotonic scheduling and deadline based one, because the rate monotonic is different. Rate monotonic is before we are going to be scheduling the task, I'm just getting the data of task A, task B, task Z. And what is the total time it is going to be processed? This is the total time it is going to be processed. Based on that one, which one is having the less time going to be get processed? Okay, so it is going to be easily processed. 3 milliseconds. Within the 3 milliseconds, it is going to be done the process. So based on that, I'm going to be giving the priority. But if you just look out this earliest deadline, it is different. Okay, if you just see this one, task 1 and task 2 is there. Task 1 is going to be completed at the 10 millisecond. Okay, and task 2 is completed the 4 millisecond. The remaining time, so it is actually running actually. Okay, if you just see this one, it is not pre-scheduled it. So just think it, your rate monotonic is pre-scheduled. It is fixed. Before scheduling the task, you are going to be telling, so this is the order you are going to be processing the task in it. But if you just see this rate earliest deadline task, okay, earliest deadline, it is not, it is a dynamic. Why it is dynamic? I'm having a three task. For example, I'm having a three task of task 1, task 2, task 3. Okay, task 1, task 2, and task 3. Three tasks I'm having, guys, simply. So this time, okay, this time what I'm going to be do is, the task 1 number is 10 millisecond, it is going to be complete the task. Task 2 is 5 millisecond need to be complete the task. Task 3 is, it's for 9 millisecond going to be complete the task. So in this time, it started. The work has been started. All the task has going to be work to be started. Okay. But when it is started to be work, the remaining time. Okay. So when it is going to be done, doing the task, it is only having the 5 millisecond the remaining time. It is having the 3 millisecond the remaining. It is having only 2 millisecond the remaining time. So when the task is currently running, it is going to be this rate earliest deadline going to be checked. Which one is going to be done very soon. So it need to be complete the 2 millis, only the 2 millisecond going to be complete the task. So for that, it is going to be done the task of task 3 first, and then do the 3 millisecond task and go to this 5 milliseconds. So which one which is having a very less millisecond? Here, if you just consider this one, the deadline time of 10 millisecond and 4 millisecond of task 1 and task 2, the remaining time is 5 millisecond and this one is a 2 millisecond. So what is actually going to be do is it is giving a priority of 2 millisecond because it just only the 2 millisecond going to be complete the task. So it is going to be done the higher priority and then go to this one, task 1. Okay. If you just see this one, task 2 runs before T1. That means task 1. Okay. I hope you got clear. And what are the pros in it? So the optimal for CPU utilization, so it is not going to be miss the deadlines if it is scheduled, because it's not like a fixed one, guys. So it's not like a fixed deadline. In this fixed deadline, you are already static when it is already fixed. Okay. So it is already fixed. You can't able to change it in meanwhile time. But you can able to change it because when the task is currently, the remaining time you can able to check it, and based on this remaining time, you can able to which is having a higher priority. Okay, so handle the variable execution times well. So that is the pros in it, right? What are the cons in it? Complex, the priority change dynamically, because when it is having a 10 task, okay, fine. If it is 100 task, it need to be checked for all the tasks remaining time. Based on that remaining time, it is need to be give the priority, so it will be stuck there. So it is complexity going to be happens, harder to implement in the small microcontrollers. Okay. And this RMS, that is a rate monotonic, is static policy. And I mean, the earliest deadline one, it is a dynamic policy. It is heavier one. Okay. Earliest deadline first is a dynamic policy. Okay. And then we are going to be discuss about the concept called as a tick timer or a stick timer. This stick timer, we are going to be clearly discuss about this card text, so no need to be worried about this. Okay, so I'm simply telling about what is a stick timer. Okay, this is core timing mechanism. Up to it, I'm just simply telling timing. So what the timing in it and what is stick timer in it? Okay, so the concept of this one is, first of all, the RTOS need the base time to measure the delays, timeouts, and time slice. Because if I'm having a time, clock in my laptop, then only I can able to see the time, and based on that I can able to do my task, do my works. Same for it requires for your microcontroller, your operating system also, right? So this case, I need the time. I need the time to be how much, if it is a delay going to be happen, if it is, for example, the delay going to be happen, the delay is called as a 10 millisecond delay. It need to be count that delay. Okay. If it is timeout is going to be happen, it need to be 10, only the 1 millisecond is there to we get timeout. Up to it, if you got clear, guys, just post clear on the chat box. Okay, just post clear on the chat. Yes, so many people have been posted super clear. So Adarva, so Vishnesh and Mukesh, Super Mukesh and Sunil, super clear. So Shivam Singh, Aishwarya. So thank you for all the people who have posted got clear. Okay. So yes, guys, we'll move back to this concept again. Here, I told you like, so it just having a, some clock to be measuring the things, right? So measuring your delays, timeouts, time slicing. Because if I want to be measuring the delay, so how much time I need to be let it. So how much time I'm having. So here I need to be finally for what? It just timing slicing. When time slicing means if I need to be slicing the time, if I'm having a task one and task two, I need to be slice the time. So 10 millisecond for this one, 10 millisecond for this one. So for all those, I need the timer, right? So here, this provide periodic interrupt. Usually, hardware timers is stick in the ARM cortex. So normally, in every microcontroller, we are having a timer, guys. So we know that what is the purpose of timer? Just counting the times. Okay, it's just creating the delay. So all the thing it is going to be happen. So here also we need the timer in it. So if you are using a ARM cortex, especially inside the processor, inside the ARM Cortex M4 processor, it's just having a system timer. It is a special timer. Okay, so kind of the microcontrollers by microcontroller it is going to be varies. Okay, currently we are just looking out the this ARM Cortex, so that I'm just telling an example. It's just having a special stick timer in it. It helps to be tick frequency. It is going to be counting the frequency. So each tick which is causing an interrupt occurs. The kernel increments the internal tick going to be counted, and it checks for delayed task whose time expired moves from the block to ready state. It preempts the schedules may be switched. For all those things, guys, for all those things, you need to be clock. Yes, the oscillator is for to only producing the clocks, guys. You don't confuse it. You don't get confused. Okay, because the oscillator is only going to be producing the clocks. Who's going to be counting this clock pulse? Your timer and your system timer only. It only can able to counting how much clocks. So based on that, it just putting the values. Okay. So all those purpose, we are going to be using this timers. So free RTOS example. So if we are just putting 1000, just indicating 1 millisecond tick. That means this is just a sound, just producing this that much amount of clock it is going to be provided. It is counting only based on frequency. You are going to be taken based on time. You are going to be utilize this formula. Frequency is equals to 1 by 10 because frequency is always inversely proportional to time. Okay, so use this time. You are going to be measuring your time as well. Okay, you are going to be measuring the time and frequency as well. And tickless mode. So you can able to saving the power also. So you can able to disabling that is tick for to saving your time. Okay. In summary, what we have been learned here it is first we have been discussing about the cooperative. Okay. First we have been discussed about the cooperative. It doesn't have any preemptive. So you just clearly look out this point, guys. This is important summary. Whatever the thing which you had discussed up to it, I'm going to be tell you the summary. Okay, just keep it on your mind. So first, we saw the type. First of all, we have been discussed about the cooperative. The preemptive, there is no preemptive because it is going to be happen periodically, one after next. The priority based, we are going to be manually scheduled it, not get any preempt. Okay, meanwhile, deterministic very low because we can't able to predict it when it is actually going to be completed the task. And use case simple and non-real time. We can't able to use it not real time. And a preemptive. Next type is preemptive. Preemptive is, yes, it is can able to preemptive the task. And the priority base, yes, when the higher priority task is coming, it just halt the current working and just giving the higher priority. And deterministics, yes, it is highly deterministics. We can able to prioritize deterministic the value, and we can able to using the hard task core mechanisms. We can able to using the real-time operating system. And round robin technique also preempting because it's preempting the task, right? Time slice with same priority. So the round robin, you just keep it on the mind. It is only going to be happen in the same priority task. Okay. And then deterministic is very less because we can't able to tell when the task is actually going to be completed. Because if you are having scheduling the 5 millisecond, 10 millisecond, your task, we can't able to predict it. Okay. We can't able to predict the task is going to be completed with this time. We can't able to do this, right? So that is, it is round robin technique is very medium and fairness among the players. And rate monotonic, the rate monotonic one is, it is static. Yes, it is also going to be preempt the task, and it is very static. And then it is very deterministic, very high, and a periodic real-time task. Okay, here also you can able to preempt the task. Here, finally the end. This is the deadline. So very end deadline one. So it is a preemptive is also possible. It is a dynamic and very high deterministics and advanced deadline control going to be happens here. Okay. And we will see the practical things in this upcoming session. So we are going to be implement all the stick timer. We are going to be implemented the timers and all those scheduling parameters in this upcoming sessions. So try to be install your STM32 Cube ID in your laptop. And I already told you the how to configure a free RTOS on your STM32 Cube ID. So you are going to be purely do this all this concept. So that's it, guys. I hope you have been really enjoyed this today's live. So thank you for this one.